to another IAEI News Live. My audio's working today. This morning it wasn't. All right, well, we are going to talk today. It's Tech Tuesday here at IAEI News Live. I want to give you a little update on, I was at the Correlating Committee last week, and you all know that because you knew I recorded our session last week. But today, I want to talk about the single line diagram and how important it is and what you need to know about it and how you need to raise it awareness of its importance. And you know what? It all starts now. All right. Okay, well, thank you for joining me today. Hopefully everybody's doing good. And it's coming to the mid-February. It's crazy how fast this year is going. And I don't know about you, but it's just screaming by. Last week, I had the pleasure of being in Quincy, Mass, and was able to attend. Yes, I am really live, Mr. Froming, Steve Froming. Yes, I am. And this is a live session of IAEI News Live. And I got to remember, please don't forget to subscribe. You got to subscribe, hit the bell to this YouTube, IAEI's YouTube channel. I don't know if you were able to catch Rudy's 10 to 10 to 10 to 10 to 10 to 10 to 10, or no, actually he did a quick update that just got a ton of views. I mean, he's a rock star. It was awesome. But giving an update, Rudy is still obviously trying to be as transparent as we can be with regard to our process, our progress at in our efforts to help IAEI get us to another 125 plus years. So, hey, Michael Hofkin in the house. Don't forget, check out the YouTube site. Don't forget to subscribe and make sure that you check out Rudy's messages, Rudy's 10 at 10. If you're not checking those out, you've got to, because he shares a lot of really good information. All right, so Correlating Committee. I'll tell you what, it was great to be back in person again out in Massachusetts. I flew into Boston, no troubles flying, wearing the mask, all that jazz. I'm just sitting around the room watching the event just like a spectator. And excellent. Thanks for the subscription. Excellent. Get out there, hit that thumbs up. And if you're going to hit the thumbs down, you got to hit it twice. Just saying. Correlating Committee went very well. It went, I believe it was, I flew out on Monday. It was a Tuesday and Wednesday, and I came back Thursday. It was a half day Thursday. So 2 full days and a half day. The Correlating Committee did a great job. All the task groups basically presented their actions. They've cleaned up some definitions. I know David Williams, the IAEI representative on the Correlating Committee, did a smash-up job on addressing all of the style manual issues, especially around definitions. All those definitions are moving to Article 100. Interesting development, I thought. There were some definitions that were similar, but not the same. Sometimes a word would change. So you'll have maybe 3 definitions of the same term in Article 100. And I was trying to figure out how is the Correlating Committee going to reconcile that, right? Because I can't define a term 3 different ways. And you know what? We're defining a term 3 different ways. And the interesting thing is, remember what we're doing. We're moving the definitions from, say, 517 to 100, 500 to 100, 700 to 100. We're moving all of these definitions up to the front of the book. And what was interesting was the fact that they recognized that whenever they move that to the front of the book, you'll see at the end of the definition, the article. If it only applies to a single article, then that definition will have the article number associated with it, as well as the code making panel who's responsible for it. So what they're going to do, if you see a term, if you're looking at a term that's used in the NEC somewhere in the back of the book, and you go to Article 100, and you find that there are 3 definitions, you've got to think about what article were you coming from, and make sure you get the right definition. Next cycle, I'm sure there will be a task group to try to come up with a combined content for those definitions. The correlating committee, remember, it's correlating committee, not technical correlating committee, so they could not make technical changes at this meeting. And so there were times where they would love to have made some slight changes and moved those definitions together and into one term, but you just can't do that as part of the correlating committee. So that will probably be a task group work for the next cycle, which is a really interesting advantage of being of monitoring or going to the correlating committee meetings, because you get to see all the task groups that are being formed and why they're being formed. So, and again, you're 3 years plus in advance of the next cycle. So anyway, really great meeting. Great to see people in person again. I'm a love-hate relationship with getting in that big silver tube and flying somewhere anymore. I am enjoying not flying as much, but you got to do it. So don't forget to check out Rudy's 10 at 10. And I will say that's what is in cycle right now. 70B public comments ended last week as well, on Tuesday, I believe it was. So 70B public comments are over. I believe they got over 700 public comments, somewhere in that ballpark. We haven't hit the 4 digits, but we're well into the higher end of the 3 digits. And remember, 700 comments, that's one committee. That's not like, for example, I'll just give you an example. I believe panel 2 had like 250 public comments. It took us a week to get through them. Now, we argue about AFCIs and GFCIs and all this other good stuff. But I'm sure we're going to have a lot of work to do on 70B. So we got over 700 as a committee. That's a lot of work to do. But stay tuned for that. 70E still hasn't published the first revision, to my knowledge. And the reason I bring both of these up is because in our session today on the one-line diagram, we're going to be talking about the one-line diagram, and we're going to be referencing both of these documents and 70B. If I had a third arm, I'd throw that one up there too. But I just want to bring to your attention that these, I call it the trilogy of the documents, because 70B, 70E, and the National Electrical Code all work together to increase electrical safety. So let's talk about what we're here to talk about, which is the single line diagram. Very important document. I can't stress it enough. In my opinion, I have, in my career as a power systems engineer, I've done a lot of short circuit and coordination studies, worked with various types of plants, industrials and commercial, and power plants. Nuclear Crystal River Unit 3. I was down in Florida for 3 years, worked on Crystal River Unit 3, and the drawings are a very important part of understanding your power distribution system. In more ways than one. As an electrical engineer, I saw value in it in certain ways. As an electrical contractor, you will see value in it in certain ways. And as an owner of a facility, you're going to see value in the single line diagram in a different way. And it's a single document, unfortunately, that doesn't get love in throughout the cycle of the development. So the single line diagram plays an important role in doing your calculations. I mean, if you're a power systems engineer and you're doing a short circuit calculation, a selective coordination study, load flow analysis, I'm trying to think of other types of studies that we do, on the power distribution, your arc flash analysis, right? So think about, if I'm going to do, hey, Lou, Petrucci, good to see you, buddy. Just think, if I'm going to do a arc flash study, I need to have what? I need to have my selective coordination. I need to know what my trip curves look like. I need to know my available fault current. Hey, Joseph, Jody Wages in the house. Thanks for joining, brother. I need to know my available fault current, and I can't calculate fault current without what? The one-line diagram. So the single line diagram is the starting point for many things. And the single line diagram, in some cases, you know where it begins? It begins on a napkin, probably in a bar, where two people are sitting there talking about a new building that they're going to build. And the electrical guy goes, wow, you know, you're going to need, this is what you're going to need. Let's draw it out. You're going to need this. You're going to need that. And they grab napkins and we draw it out on napkins. And then we go back to the office and we put it in CAD, AutoCAD, or some sort of software, right? That's the flow. So, and when you begin your one-line diagram, you haven't purchased a doggone thing. Hey, Mark, we just talked, Mark Gandles. You haven't purchased one electrical product. You haven't even broken ground, and you're already working on the one-line diagram. So the single line diagram begins very early in the design process. And unfortunately, it gets attention up front for a lot of obvious reasons. You're going to go out to bid and out to quote. So I'm going to need to know my numbers. I'm going to need to know what the cost is for my installation, right? I'm going to need to know what my, I need to communicate with my suppliers and say, look, I need a quote. I need a quote for a, for my power distribution system. Nihad El Sharif in the house. We're talking one-line diagrams. I know you and I have talked about this before. You're going to build the single line diagram to go to your suppliers, and they're going to look at that diagram and figure out, okay, I'm going to work a quote up for you. And you're going to have multiple manufacturers doing the same thing. They're all going to be quoting against this one-line diagram. Then they're going to get the order. You're going to award the order, and then work is going to start getting done. And that diagram has to go through a life cycle. It's born probably in a bar or in a restaurant, and then it grows into something that goes out for bids, and then that same document is used during the installation process, and maybe changes are made, and then you should have as-built drawings. And then after the as-built drawings, you should be moving into the longevity of the power distribution system. And everybody is going to get value out of that single line diagram throughout the entire process. And remember, it's fluid until you get your as-builts. It's fluid until that electrician lands the wires on both sides, has all the raceway in place, has all the equipment on the wall, and they gaze on perfection and walk away. It's fluid until the job is done. And we need to document that process. We use it for safety evaluation studies. What would I use a one-line diagram in regard to my safety plan? We're going to talk about 70E and lockout tagout, 70E requirements. We're going to talk about the National Electrical Code has provisions that says you have to lock and you have to have provisions for a lock in certain applications. And it gives us rules with regard to that the lockout mechanism has to remain with the circuit breaker, right? So it gives us rules with regard to the installation of that resource. Why? Because someone is going to use this to lock and tag it out, and maybe while they're using 70B to perform maintenance, and just maybe they need to know what to lock and tag out. So that's what this document is there for. Efficient maintenance, and enough said about that. Terminology. Now, okay, I am guilty of this. Guilty as charged. And I know most people who reference this document are just as guilty as I am. What do we call it? The single line diagram. We call it the one line diagram. Go give me the one line. Go give me the single lines. I've heard people call them schematic diagrams. I stay away from that term. And the reason I stay away from schematic diagrams is because typically a schematic is associated with a piece of equipment. You could say that the schematic diagram is a one-line diagram of that equipment because it shows you the power flow. It shows you everything that's connected. But when you say schematic to somebody, I'm looking at a piece of equipment. If I say a single line diagram or a one line diagram, I'm thinking power distribution system, all the big stuff. So I'm going to use those interchangeably throughout our time together today. So some codes and standards. We said 70E. Why would I use it in 70E? And I'm going to go through the sections in 70E. 70E tells me I need to lock and tag things out. And there's various reference in chapters 1 and 2, and possibly in chapter 3. Maintenance. Chapter 2 is your safety related maintenance requirements. And, that's going to be important from a 70E perspective. The National Electrical Code, we already said, there are some requirements in here. Very little, though. Very little reference to the single line diagram in 70 in the National Electrical Code. 70B, I'm going to talk to you a little bit about some of the where we're at in the first draft for 70B on maintenance, and it's getting a little bit more meat. What I think the key takeaway as we walk through this document, these three documents, and we talk about, I am going to say requirements in quotes. And the reason is it's very hard to find in any of these documents language that says thou shall have when it comes to the single line diagram. Now, you can't possibly achieve some of the goals of these documents without having that document, but none of these documents have gone out on that limb to say thou shall have. There have been public inputs and public comments to get that language in these documents, and they've never been passed. So, and the reason I say that is because in my mind, it is very important, especially maintenance individuals in facilities who know updating these diagrams, it needs to be budgeted. We need to have money for that. Maintenance, we need to have money for that. Maintenance of the one-line diagram to keep it up to date. That's a maintenance feature, especially after the initial construction. So we need to fund this. And I've had maintenance people call me, and I've done a lot of educations, especially in healthcare, talking about the importance of the single line diagram. And the biggest complaint I always hear is, I don't have money to update it. Or even during the construction process, hey, it's the last thing, the as-built drawings. And you know what? We ran out of money. We spent it on change orders for whatever reason. And there's never any money in the budget to update. So that's right. Schematics are the single, and the one line diagrams are your more general. Absolutely. So you got to be careful on the terminology. But typically what people are looking for, and they'll say, Tom, show me in 70E where it's a requirement that I have to have the single line diagram. Show me in the National Electrical Code where it says thou shalt have a single line diagram. And I'll tell you what, I set out, I took the challenge on, and I said, I'm going to do it. I'm going to help you. And they asked me for an educational program on the single line diagram because they wanted to raise that awareness with their bosses to say, look, I need to put some money in the budget to pay somebody, even on our own staff, It's not necessarily, you don't need to go out and hire anybody to update your single line diagram. What do you need? You might need a copy of AutoCAD, maybe. I don't know. Maybe you just need a copy of Adobe Maker. I don't know. I don't think it's very expensive, especially if you have the manpower and you have the budget to give him the hours to make sure your single line diagrams are up to date. And I like your point of view. You are absolutely correct. And that's the way I read and I reference schematics. That's why when someone says, hey, I need a single line diagram, and Article 100 of 70E defines a single line diagram as shown. Dean Austin, you're right. You know what? I got to make t-shirts up that says that if you don't schedule maintenance, your equipment is going to schedule it for you, coming in off of Facebook. Thanks for joining us, Dean. No, you are absolutely, that is spot on. I love that tagline. I tell you what, if I was in business, that'd be on my truck. That would be on my truck. Oh, I love that. I love it. So, single line diagram. And what I'm doing is I'm opening my book just because. Remember, I told you it was a while ago. Somebody asked me, "You stole it." All right, that's okay because I'm going to steal it from you. Single line diagram that shows single line diagram. I'm going to make sure that definition has not changed, and it hasn't. The single line diagram is a diagram that shows by means of single lines and graphic symbols the course of an electric circuit or system of circuits and the component devices or parts used in the circuit or system. Now, when we say a single line, why would I have anything other than a single line? There are such drawings as 3-line diagrams. And you might say, why would you have a 3-line diagram? I have phases A, B, and C. And in some cases, especially medium voltage, where I have relays, or even low voltage where I'm using CTs, and I want to demonstrate the wiring of a relay with relationship to the CTs and how the CTs are wired in Y or delta, I will, and where the dot needs to go on the positive and negative, how the current will flow through the circuit, I will draw those on what we call a 3-line diagram. They get very busy. A 3-line diagram can be a challenge, especially if you've got attention issues. I mean, I know an individual who, when they look at something, they see everything. They don't see specific items like you and I may. Like if I look at a 1-line diagram, I can look at individual components. There are some people that have a hard time taking in single items. They take in the entire drawing and they get headaches. And it can be difficult to read sometimes, and especially 3-line diagrams. They'll get very busy. You've got phase A, B, and C. You'll have all of the individual CTs in each of those phases and any relays. Sometimes you might take a CT off of maybe only 2 phases, etc. So, and what we do in a single line is we combine all 3 of those lines into a single line. It represents A, B, and C. So if you see a CT around a single line diagram, more than likely you have 3 CTs there, not just 1. You have 3 CTs on one on A, B, and C, maybe 4, because you might have one on the neutral as well. It depends on the system. Or you absolutely may have one big 0 sequence CT. So you can't take from a single line diagram information that you might need off of a 3-line diagram. Okay, the single line diagram has a sole purpose. It helps us understand how the flow of current is through a power distribution system. Remember, it says the course of an electric circuit or system of circuits and the component devices are parts used in that system. It helps us understand where, say, a transformer is in relation to equipment, how it's fed, etc. That's how the 70E defines it. And this is an example of a 1-line diagram. So what you got up here, what you'll see is you notice I have the utility defined. you'll notice that I have, so I have the utility. I have some information around that transformer. I know it's a delta Y ground transformer. What does that tell me? I mean, just that alone tells me how my system is or isn't grounded. Tells me how I need to treat the rest of my equipment. It helps me understand my voltages. The fact that I have a neutral point in my system tells me I have a 480 volt line to line, and I have a voltage from line to neutral. It tells me my voltage of my power distribution system. So the single line diagram is going to have information on it that I will need for power system studies. I need to know that 5.75% impedance. I need to know those voltages for proper selection of my overcurrent protective devices. So if I get this out to a supply house, they're going to know I need 480 volt breakers. And when they see that ground right here, they're going to know which breaker. And if this was a delta or a corner grounded delta, they're going to know what overcurrent devices they can and cannot use. Why? Because of the one line diagram. And just think if you messed it up. Just think if you did a copy paste of that delta and put it here, and now you're out getting specs back on a delta system, an ungrounded system. You might get somebody come back and say, hey, you got an ungrounded system. I'm going to quote you because the code requires an alarm system and the monitoring of for ground faults. Why did they quote that? Because you screwed up the drawing. Drawings are very critical and very important. They'll be stamped by a PE when they're done, hopefully. So, and what else do I know? Available fault current. Why would I need to know the available fault current? Because I need to pick the right overcurrent devices that can interrupt that fault current. I need to purchase the right assemblies that have the right short circuit current rating. Now what I've seen some people do, they'll take this one line diagram and they'll say, I'm going to put 65 here. I'm going to put 10 down here because this transformer, I'm going to put 10 down here. And that's how they label it. And then they say that's the interrupting rating. So they'll label the equipment with interrupting ratings instead of estimated available fault current. Because remember, if I'm going out to bid, I haven't broke ground. I haven't purchased anything. This transformer, the transformer that I'm showing right here, when I am going out for bid, I put 5.75% impedance. Where did I get that number? I got that number from IEEE standards that says your average impedance for a transformer is going to be 5.75% for certain sizes. If it's a much smaller transformer, it's probably not going to be 5.75%. So the IEEE standards, when I'm doing my design, will get me in the ballpark. And I want to make sure that I'm in a ballpark for that impedance, that it's not, my transformers aren't going to come in with a lower impedance and bump the fault current up higher than what my interrupting ratings are or my short circuit current ratings are of equipment, right? So that's a little game you have to play, and you have to estimate the conductor sizes because when you start getting down into the power distribution system, there are conductors. You haven't pulled a conductor. You need to estimate the lengths of those conductors, estimate the lengths. And how do we do that? We look at our plan views.
Sorry, I couldn't understand, but I may have a few...
Alexa, stop. I love her. She's awesome. But every now and then she speaks when she shouldn't. So what do? I have to estimate my conductor lengths. And how do I do that? I will go to the plan views that an architect, the architect will put together the layout of the buildings. Could be a campus environment, could be a very large commercial building, could be an industrial facility. I will know where my service comes into play. I'll have an estimate of where this panel board, where that transformer is going to be. I may say that transformer is going to serve industrial control panels for a manufacturing line. I'll look on the plan views where that manufacturing line is going to be. I'll figure out where I'm going to put that transformer, and then I'll trace out, I'll say I might take as the crow flies and then add a percentage, or I might just do some rough estimates. I know I'll probably go over and go up this way and maybe go up vertical and down horizontal, or up vertical, down vertical. Maybe I'll have a couple horizontals in there, and I'll estimate the length of that conductor so that I can get a ballpark figure in my available fault currents for my power distribution system, so that I can then go out for bid for equipment that is realistically rated. I wouldn't want to have to buy a 65K rated breaker when I only need a 10K rated breaker, if you know what I mean. So the one line diagram will see a life cycle in the early process. And on the one line diagram, you're going to have your overcurrent protective devices. You're going to have your motors, your large equipment. You don't typically see machinery. We don't put, ceiling fans and, receptacles on a one line diagram. We go down to the panel boards. Maybe in an industrial control panel if they're large enough. Maybe the motors. Where do you find the industrial control panel information, like off of, say, that panel board and some of the smaller loads? Panel schedules. So what you'll do is you'll do a one-line diagram, and then you'll marry that with panel schedules so that you can do your load calculations, make sure you have the right, figure out what size mains you need or what size panels you need from an amp rating perspective. And then you'll draw a line. Basically, we represent a panel board or a switchboard with a line, and sometimes you'll see the dotted lines drawn around it, and most often you don't. You just see a line, and that bus represents a piece of equipment. And the conductor lengths and the conductor sizes, there's usually a schedule, sometimes on the drawing, maybe sometimes a part of a separate drawing that has just a list of conductors, and all you'll see on here was maybe a C1 or C500, C6. There's just a C for conductor and a number. And then you go to the schedule and you'll see C100 is, 4 5-watt conductors, 1 per phase, 560 feet, and that'll be an estimated number. And what I used to do on my drawings, I would put the impedance value, the ohms per 1,000 foot. Why? Because I wanted to make sure I had the information I needed for the next phase of my short circuit study, which was my impedance diagram. So these diagrams are going to have all of your transformer and the pertinent information, all your motors and pertinent information. Large motors, you'll have an impedance. Smaller motors, they typically just lump them. 20 horsepower, 25 horsepower motors, they'll say this is a group of 25 horsepower motors, and so we have 600 horsepower combined. Okay, and they'll model it as one motor. Larry Griffith, thanks for joining us, Larry. Really appreciate it. We're talking one-line diagrams, brother. Welcome to the team. And the importance of that. Right now, we're just talking about what's typically on a one-line diagram. You'll have the conductors and pertinent information, like the number per phase, the length, whether it's copper or aluminum, the raceway, if it's steel, if it's plastic, if it's in cable, if it's in tray, air. So you'll have important information associated with those conductors. Your overcurrent protective devices, the fuses, what size they are. Sometimes you'll have the fuse and you'll show the switch, the rating of the switch. I'm not showing the switches. Bad boy. I should have had the switches in here too, but you know why? I don't have enough room on my PowerPoint slide deck. You get the gist. You need to know your overcurrent devices. If it's a circuit breaker, if it's a fuse, if it's a circuit breaker, what is the rating? And sometimes you'll see something that says 400 AT slash 200 or 400 AF slash 200 AT. And you say, well, what's AF and AT? It's a 400 amp frame breaker, but it's adjusted down to 200 amp trip. It's important to know. That tells you a couple things. It tells you, A, it's an electronic trip unit. You might even see ETU or T/M for thermal mag. ETU is electronic trip unit. They'll put ETUs, they'll put thermal mag, they'll tell you if they have ground fault, they'll tell you if they have arc flash reduction technology on them. And that's pretty much, so you want enough information you have to think about, what am I using it for? If I'm going to send this out for bid, right? The supplier is going to look at that overcurrent device and say, okay, I have a circuit breaker and it has ground fault. Now they know they need to have a ground fault, not just because it's 1,000 amps and above. I mean, I can put ground fault anywhere I want to, ground fault protection of equipment, but you need to tell whoever it is, and you'll do that on the one-line diagram. Maybe you want an arc reduction technology on there, so you'll say AF or some other designator. There's no standards. In most cases, there's no standards. There are some standard nomenclatures that we'll use, but I've seen engineers get creative in saying this is what I want here, because they want to make sure that they get the right quotes. So the one-line diagram is complete a one line or single line in conjunction with the physical plans. You need the physical plans, and also those. Hey, Robert from Omaha, you're the man. Talking one line diagrams, talking about the fact that you're going to have a one line diagram, but you're going to need the plan view, and you're also going to need your panel schedules. In some cases, which I didn't mention earlier, I probably should have. In some cases, they might not even call it a one-line diagram. The other term I've heard used, and it's a different type of diagram, a riser diagram. You'll see that in commercial buildings, high-rise buildings, tall buildings. You'll see down the bottom the power distribution system, and then they show you that tall building, and they show you the busway going to the top and where the taps are taken off, the transformers on each of the floors, and where the panel boards are, and how many panel boards. And they go up, and they call it a riser diagram. They'll show you the floors. What does that help you with? Lengths. If you know the height of the building, if you know the distance between floors, you can estimate length of conductor or length of busway that you're going to have in place. And yes, it needs to be up to date, Robert. Absolutely. You need to have the utility supply, primary utility supply transformer. Sometimes I've seen just a line that says utility, available fault current, X to R ratio. You're going to want all of your switchgear, your panel boards. I would say, junction boxes, sometimes we put them on there, sometimes we don't. I don't know. I've seen people go both ways in that. I never put junction boxes in my one-line diagrams. That was for the electrician. And the reason, it didn't add any impedance. And typically, any junction boxes that were planned, that's not something I'm going out to bid for. That's going to be purchased as we go. Relays and other protective devices, normal operating modes of switching. So you'll have NO, normally open, normally closed, especially if you have tie breakers or anything like that. You need to know, like transfer switches, the normal operation, emergency operation. And in some cases, if you have a three-way where you can have a center, a switch that can put it in the middle where you don't have the supply coming from anywhere, you need to see that as well. Your capacitors, your modes. We use one-line diagrams for things like this. So in this case here, if I'm working on the secondary of a transformer, and this is it's a pet peeve for me. It really is. Most dangerous place in a power distribution system is that first panel board, that first piece of equipment on the secondary of any transformer. Why is that? The incident energy is based upon the line side overcurrent protective device. And why is that bad? Well, I picked that overcurrent protective device on that transformer, not because of full load amps. I picked that device to make sure that the inrush currents of that transformer don't trip the circuit breaker. So I will inflate the size of that molded case circuit breaker, and I'll inflate the size of the conductor on the line side of that transformer. If I have to selectively coordinate through this transformer, I might have to go up as high as 250% on that primary overcurrent device. That moves the instantaneous way over to the right. This is no different than a utility application, service entrance equipment. Imagine that line side breaker being the fuse up on a pole on the line side of a transformer that's feeding the structure or whatever it is that you're feeding. The same problem, the same reason I have a very high incident energy at service entrance equipment is on the secondary, or the same reasons the incident energy on the secondary of every transformer in my system is high. So if I'm going to perform electrical work, I need to know that I'm working on the secondary of a transformer. If I'm doing justified energized work, Robert, you know all about that, right? If I'm doing justified energized work, then I know I'm on the secondary of that transformer. I can walk out, and they call this moxie. I could walk out to this piece of equipment, and if I looked at this equipment and I saw 0.5 calories, I'd know that label is wrong. Why? Because they probably used the main device in this panel board to determine the incident energy and not the primary overcurrent protective device ahead of it. How do I know that? Because I have a one-line diagram. And I know incident energy calculations. And I know the energy on the secondary of this transformer is going to be, in West Virginia, we call them a biggin. It's a biggin. 23.5 calories. Now, if I'm what a good phrase. Greetings from Costa Rica. Excellent. Yes, I agree with you. That is a really good phrase. Your equipment will tell you when you don't maintain it. Now, when I look at this design, I could sit now, if I looked at this and said, well, you know, the design engineer broke out the main overcurrent protective device and put it in its own enclosure. Maybe it's a circuit breaker in a box or a fusible disconnect switch. And look at the calories in this panel board. Look what I did. I went from 23.5 calories per centimeter squared. I simply removed the main overcurrent protective device and relocated it into its own enclosure, and I took it down to 0.25 calories. That's a design change. It's not required by the code. But if I'm working on this equipment and I look at my one-line diagram and I know I have that overcurrent protective device, I know that that number is real. If I saw 0.25 calories over on this one, I know they did the math wrong. Are those instances out there where the math can be done wrong? We're all human. A one-line diagram is your road map to getting your destination, and without it, you are lost. It's no different than looking at an old map and trying to get somewhere. Looking at a map that's out of date where there's new roads out there that you didn't know about it and you need to get from point A to point B, and you're following an old map. To following the map that we have these days, which is on our phones. Those maps are awesome because they're up to date and real. Let's take a look at 70E. Signal line diagram, we already talked about the definition. That's right out of 70E. Lockout, tagout. 120.2, and I'm going to make sure that I got the right references. 120.2, lockout, tagout procedures. Right? Look what it says. Lockout tagout procedures shall be developed on the basis of existing electrical equipment and systems and shall use suitable documentation, including up-to-date drawings and diagrams. Now it says to use suitable documentation, including up-to-date drawings and diagrams. It doesn't require you to make a diagram. E says, now that's 120.2. Electrical interlock, that should not be 120.2, that should be 120.4. And I'm going to look at the numbers. There's B. Some of these have changed. And this is one of them. Lockout, tagout principles. Electric circuit interlocks. That is not in. Oh, principles. Yeah, 120.2. Ground device, electrical, it's D now. So in this version, that is D, electrical circuit interlocks. Documentation, including up-to-date drawings and diagrams, shall be reviewed to ensure that no electrical circuit interlock operation can result in an energizing the circuit being worked on. Not in. You don't want to be in the circuit. You want to be working on the circuit. 120.5, let's take a look. Make sure I got the right titles. 120.5. 120.4. What's the title of this? Process for establishing and verifying electrically safe work condition. I believe that is now process. Lockout, tagout procedures. This is establishing and determine all possible sources of electricity. I have to use the one-line diagram to get that done. And that's on page 70E-23 of the latest version of this, the 2021 version. You have to determine all possible sources of the supply. You have to, after properly interrupting the load current, open the disconnect device for each source. Wherever possible, visually verify all blades of the disconnecting device, etc. Release and stored energy, blocked energy, apply lockout, tagout. You can't do any of this without an accurate one-line diagram, because how are you going to determine all the possible sources of electrical supply to a specific piece of equipment if you don't have a one-line diagram to help you with that information? .205, single line diagram, 205.2. Let's check out 205. Chapter 2 is on maintenance. General maintenance requirements, single line diagram. A single line diagram where provided for the electrical system shall be maintained in legible condition and shall be kept current. But you know what the problem I have with this? Where provided. In my opinion, that should be shall provided. But, and let's take a look real quick. I am going to look at the latest version. And it says a single line diagram where provided. So it was not, there were no changes made to that section. So it still says where provided, not shall be provided. 340, chapter 3 now, 340. 340, Article 340 is titled Safety-Related Work Practices, Power Electronic Equipment. 340.5, specific measures for personnel safety. And look what it says. Necessity of reporting, number 6, provisions of complete and accurate circuit diagrams and other published information to the employee prior to the employee starting work. The circuit diagrams should be marked to indicate the components that present an electrical hazard. Curtis, welcome, Curtis. Off of Facebook, this is a comment. What about the control panels being built at some facility and never being inspected? You know, that's a good point. I think you're talking about when it's built internally at that facility, probably not gone under a UL 508 analysis at all. E3 now, informative Annex E. Let's take a look. What's the title? Informative Annex E, Electrical Safety Program. You think it might be important? E3 says typical electrical safety program procedures. Electrical safety program procedures can include, but are not limited to, the determination and assessment of the following. And one of those items, electrical single line diagrams. Very important document. Just doesn't quite say thou shall. 70B. Now, 70B is going through a big transformation. If you're not aware of it, big transformation. It's moving from a, you could, and, you might want to a you shall document. And that solidifies that trilogy of installation, safe work practices, and maintenance, all three of those. The single line diagram is mentioned here. The work center of each maintenance group should be conveniently located. This work center shall contain the following: copies of all inspection, copies of previous reports, single line diagrams, schematic diagrams. There's a difference between single line and schematic. And if you want to know, there was a really great chat. Scroll through the chats, and I believe it came from Facebook. I'm just looking through here. Yep. Nope, through the YouTube channel. So you got to go out and subscribe. You got to subscribe to the YouTube channel. All right. 6.2.2, diagrams. This is chapter 6 in 70B, planning and development of electrical preventive maintenance program. The availability of up-to-date, accurate, and complete diagrams is the foundation of a successful electrical preventative maintenance program. The diagrams discussed are some of those in common use, and I don't know if I have those numbers in here or not. Single line diagrams. And this tells you what they should have. Electrical equipment in the power system give all pertinent ratings, basic voltage, frequency, phase, nominal operating position. And we talked about all of this. Available short circuit current, all over current protected devices, types. I will tell you that in the chapter 6 of the new 70B, in the public, the first draft, you all can go up and take a look at the first draft. Take a look at chapter 6, section 6.1.2. It says, up-to-date single line diagrams shall be the primary reference for the system study. The single line diagram shall be maintained in a legible condition. The single line diagram shall be kept accurate. The single line diagram shall indicate the date of last revision. And it says, when single line diagrams are not available, the facility or equipment owner shall be responsible for providing an equally effective means of obtaining the necessary information. I would love to see, I should have put a public comment in to delete 6.1.2.4 or modify it to say, when single line diagrams are not available, the facility or equipment owner shall make them available, right? Because they are that important. They are just that important. So in chapter 6 of the new 70B, we address single line diagrams specifically. Now, the National Electrical Code. All right, National Electrical Code, they've got a 490.25. And I'm going to grab the latest book because you never know. 490.25. And here's the thing. This is what I'd love for you to do. If you are trying to help senior leadership understand the value of the one-line diagram, I'm giving you all the references in 70E, 70B, and the National Electrical Code to build your argument. Now, Article 490 is equipment over 1,000 volts. 490.25 is still there. It's called backfeed. Installations where the possibility of backfeed exists shall comply with A and B of this section. They need to have a sign. So they reorganized this in the 2020 code. They said a sign, a permanent sign in accordance with 110.21b shall be installed on the disconnecting means enclosure or immediately adjacent to open disconnecting means with the following words or equivalent. Danger contacts on either side of this device may be energized by backfeed. And diagram is B. A permanent and legible single line diagram of the local switching arrangement, clearly identifying each point of connection to the high voltage section, shall be provided within sight of each point of connection. So now this is in Article 490, and the scope of 490 is it covers the general requirements for equipment operating at more than 1,000 volts nominal. More than 1,000 volts. Okay, so the one-line diagram, a very important tool for servicing, short circuit calculations, coordination studies, load flow studies, safety, all other engineering studies, your electrical safety procedures, and efficient maintenance. Lockout, tagout is critical. Now, what I'd love to do in the last 4 minutes. 4 minutes. No. 6 minutes. What am I talking about? I got 6 minutes. The impedance diagram. So the other important diagram that the one line gets you to is what we call the impedance diagram. Power systems engineers use the impedance diagram to calculate things like fault current, to understand X to R ratios. And you may not know what that is, or you may know what it is. But I'm going to tell you, I'm going to walk real quickly and help you understand that the impedance diagram, when I'm going to model a power distribution system, let's go back 50 years when I did these by hand, not me, when the industry did short circuit studies probably by hand, but I'm 50 years ago. I don't know, somewhere in that ballpark, maybe less. I know I did one. I did two short circuit studies by hand, large systems, just to learn. That's what my mentor had me do. You will take your one-line diagram and you will take your one-line diagram and put that into an impedance diagram. Yes, that's another important role, is your voltage drop. So you take your one-line diagram, you convert that over to impedances. And you take your one-line diagram, convert that over into an impedance, because just like you said, for voltage drop and short circuit studies, right? So we'll take this one-line diagram and convert every one of these. Now, we don't convert fuses into an impedance. We don't convert circuit breakers into an impedance, or the bus inside of that panel board into an impedance. We will convert most of the utility will be converted into an impedance, transformers, motors, conductors, busway, your generator as an impedance. Your major components will be converted into an impedance and drawn just like the one-line diagram is. And that's what we would call an impedance diagram. Not all of the power system components are resistive. Some of them might be purely resistive. Some of them might be resistance and reactance. Some we might just model as a reactance, like a transformer. We don't typically model a transformer's resistance. Not typically. If I have software application, by all means. And this is what we do. We basically are taking all of the components, creating a real and a reactive. Your conductors are in the back of the book. Table 9 in the National Electrical Code has all of the impedances. So chapter 9, table 9 has the impedance values for your conductors. You'll see your AC resistance. You'll see your X sub L. We use that for voltage drop, right? We do voltage drop calculations. I will do short circuit studies based upon these impedance values. And based upon the impedance values and establishing the amount of inductance to resistance, I know what my power factor is, which helps me with understand my energy usage, right? And I could lower my energy bill if I know my power factor. If I want to do power factor correction, it all starts with the single line and this impedance diagram. Transformers and reactors, primarily reactance. Just this portion of the triangle is all I'll model transformers, reactors, and motors. I'll model them as an X. Sometimes we'll throw the X to R ratio over and get an R value. Most often, we're doing an X. Highly resistive components, heaters, incandescent lights, big R's, resistance. That's your horizontal on your triangle is your resistance. Your conductors, if you go back to table 9, they'll tell you what the resistance and the reactance is of each conductor. And you'll model the system with a resistance and a reactance for every one of your conductors. There is never a case where you'll just do resistance or just reactance. You always will want to model both the resistance and reactance. And I'll just give you an example. You know, if you go to the table 9, chapter 9, there's your ohms per 1,000 feet. There's your conductor sizes. There is your X sub L, that's your reactance. And you'll notice it's different for aluminum or in PVC, aluminum conduits or steel conduit. And then you have your actual ohms per 1,000 foot. And then you have your alternating current resistance for uncoated copper wires or for aluminum wires. And this is why it's important on the one-line diagram that you say, is it copper or aluminum? Is it in PVC or is it in steel? Or is it in open air? And then you have your effective Zs. So that's sort of an overview of the journey of the one-line diagram. We've got to keep it up to date. We can't forget about it on our at the end of the project. Make sure it's funded. What about current limiting devices? Curtis, we don't model the impedance of a current limiting device. What we use the current limiting devices for is to help us determine incident energy and equipment protection. And it all starts with the one-line diagram. With the technology available today, Robert says there should be no excuses for not having this info. Absolutely right. There's no excuse. You can actively update your one-line diagrams throughout the entire design process. Make sure it's accurate when you're done with the build. It is critical. Plays a critical role in the life cycle of your power distribution system. Well, we did. I hope you can use this one-line diagram discussion. And you know where else? Plan review. Not everybody does a plan review. But plan review will catch issues and problems if your one-line diagrams are accurate. All right. Well, thanks for another great session of IAEI News Live. I really appreciate the dialogue. Curtis Jones for joining us. Robert from Omaha. Manar Rojas for joining us. Larry Griffith. Dean Austin. I can't pronounce some of the names. That just tells you the international capability of our program. Please don't forget, subscribe, hit the thumbs up, and click the bell. Don't forget to do that. We got to get those subscriptions up. Okay. Better to catch in plan review. Absolutely. Thank you, Lou. Thanks, Dean, and everybody else for joining in. I'm going to sign off. This is Thomas Dimitrovich signing off from IAEI News Live. Take care, stay safe, and remember, please stay healthy. Until next week.